Hi, my name's Jim Murray, and this is a lab where I do a lot of my work. I think it's an interesting possibility that this could develop into some very important progress for mankind in general. So as a result of that, I thought it would be a good idea to give a little overview of what I've been doing and what this is all for. I started working in alternative energy projects when I was 19 years old. I'm now 66, and I have spent a lot of time and a great deal of money coming to an understanding about things which most people do not choose to investigate. The result of those investigations is the type of equipment that you see all around you in this room. I'm going to be going over some of the aspects of those inventions and discoveries as we progress through this presentation. But basically, I think I should open by saying that my intention here is to demonstrate the possibility in the near future of having machinery with efficiencies that are absolutely unheard of. These things can be accomplished without violating any physical law, simply because of the fact that some of the things that have been discovered here indicate that not all of the losses which are the most parasitic in nature have actually been identified and included in the average engineering approach to the design of motors and generators. So with that, let me bring you over to the earlier section of the work I've done, and we'll progress from there. The machine that you just saw is called a Dynaflux alternator. I invented that many years ago in northern Michigan when I was working for Bethlehem Steel. And the story behind its evolution is pretty interesting, but we'll forego that to another time. More importantly, I think I'll concentrate on what the device actually does. In order to give you some insights into that, what I'm going to do is give you a really simple but effective demonstration about why electricity costs so much to produce. This is a samarium cobalt magnet. There's absolutely nothing unusual about it except for the fact that it's extremely powerful. If I drop this, it falls in the gravitational field just like any other object would. That's the whole purpose of showing you it separately, so you can see how fast it falls. This is a brass pipe. Now, when I drop this into the brass pipe, you might expect the same results, but believe me, it'll be very different, because it's going to take a great deal of time for that thing to transit the pipe. Now, the question is, why does that happen? See how long it takes as opposed to when I drop it in the open? The reason for that is that as this magnet moves through the pipe, its motion and its magnetic field create currents inside the material of this pipe. And those currents in turn produce a magnetic field of their own. And that magnetic field bucks the progress of the magnet, so that instead of accelerating at 32 feet per second, it just falls at a constant velocity. Well, the exact same thing happens in an electrical generator, except that the effects are a lot more expensive. Let me just get an armature for you to look at. This is a standard armature removed from the kind of generator that you might have being turned by a gasoline engine or a little diesel engine, something like that, so for auxiliary power in your home, for instance. You'll notice that there are coils embedded in the material here. And as this rotates through a magnetic field, there's a voltage produced in these windings. That's in concert with Lenz's law. But also, what happens is the minute you close the breaker and take current out of this device, forces appear which attempt to cause this to motor or to twist as a motor in a direction opposite to that which you are attempting to turn it. And so the prime mover, your gasoline motor or whatever it is you're running this with, then has to labor to overcome this back torque or this reverse torque in order to continue this thing turning at a sufficient speed to give you the voltage that you need to keep the current flowing. In very simplified terms, that actually is the reason why it takes so much power to turn a generator. Or, to put it in more succinct terms, the power in has to equal the power out. There isn't any advantage that you can seek which will increase the overall efficiency or reduce the amount of fuel that you're consuming. But that's only true of this particular geometry. Now I'll demonstrate a different approach. You noticed in the previous piece of equipment that I showed you, the shape was cylindrical. If you focus on this machine, you'll see that we're making use of a very unusual geometry in the rotor. It's actually an ellipse. It's an ellipse in 3D, but the cross section of that ellipse is still circular or cylindrical, and so it can rotate between two field poles without any difficulty. Now there's a very specific reason for doing this. When we create a magnetic field with this winding, the flux comes down through here, attempts to cross over to the other side and return to the magnetic coil, and this is the only path that it can take to do that. So when this is rotating, the net result is that the flux in both of these pole pieces is actually oscillating back and forth. And when it oscillates back and forth, it's moving in a direction which is 90 degrees away from the direction that is used in a standard generator to produce a voltage. So it's actually shuffling back and forth horizontally in these pole pieces and creating a voltage in these windings. And then when we close the breaker and attempt to use that current, the result is that for part of the cycle, it's going to be experiencing a resistance to motion, and for the other part of the cycle, it's actually going to be experiencing an assistance to its turning. And as a result of that, we wind up with a totally different concept in generation and very different numbers to describe the efficiency of the system. It's a very long and laborious presentation to go through all of the numbers because it requires a thing called a segregated load analysis, which I think the audience would find very boring. However, you will be directed on this presentation to lectures and other locations on the internet where you can see lectures that I've already produced and interviews where I touch more deeply on these particulars. So if you have an interest in that, be sure to follow through and look at some of the other material that's going to be available to you. I think the best thing to do at this point is to give you a demonstration of how this actually functions, and it'll become self-evident as to how different it is from a standard generator. But before we do that, I think I'll just touch on what the equipment is that you're looking at. This is a DC motor, and it has on the back end of it a tach follower, which allows the motor to be to have a reference, so it can turn at a fixed speed regardless of how the system changes. This is simply a drive belt that comes over here and runs a clutch assembly, and this clutch runs my generator, and the forward clutch runs a standard generator. And the reason for that setup is in case we want to make a comparison between a standard machine and the Dynaflux machine. Then over here we have the control console that runs all of that equipment, And in this upper chamber here is a what we call a DC drive, and that drive is what regulates the behavior of the motor. It's programmed to start the motor off at a slow pace and accelerate it at an even rate, simply because of the fact that to jerk this thing into the on position with none of this equipment being bolted down, you risk damaging something or breaking belts. So with that, I will start this thing up, and as it's accelerating, I'll tell you a little bit about the instruments that are on this panel. The top meter here is your input voltage, this is your input current, and this is the shaft speed. The two center meters monitor the magnetic field. This is going to be the generator field voltage, generator field current. This is the output voltage, the output current, and the output frequency of the generator. You can see it's already building towards 60 cycles. So when this speed reaches 1800 RPM, then we'll be ready to bring up the magnetic field. There it is now, it's about 1800. So I bring up the magnetic field. And now we're actually generating the voltage. You can see there's 24 volts coming out of that machine. And when I turn this breaker on, the two floodlights over there will assume the electrical load. So those lamps are now being powered directly by the energy that is made available by the rotation of that machine. And if we had run the other machine first, you'd be able to contrast the behavior between a standard generator and this machine, and you'd see that this hardly presents a load of any sort whatsoever to the prime mover. So I don't want to get into too much detail because, for two reasons, these lectures can go on indefinitely. There's really a lot to transmit to other people, considering I've been working at this for more than 45 years. So rather than bore you to death, I think it's more interesting to keep the thing separately from the voltage aspect. Now, a lot of the results of that are proprietary. I'm not going to go into the details, but I will show you a couple of interesting features, and we'll use that to further the explanation of the machine. First of all, there are two sets of windings in this machine. One set is brought out on this pair of lines, and the other set is brought out on this pair of wires. Now these two conductors go directly to this 300-watt bulb. The ones from this side do not come directly to this bulb. They go through this little selector switch, this little knife switch that's down here. One side of that knife switch has a copper bar across it, which essentially constitutes a short circuit. The other side will allow the connection to be made to this bulb. It's important to understand that ahead of time so that you can grasp the significance of the demonstration.